Bismillahirrahmanirrahim. In this video, we will talk about the heap data structure, right? So, before going to study about heap, let us understand one important concept that is called uh, binary tree, right? So, binary tree is different from binary search tree. Um, Although the binary search tree is also a binary tree, but this is a bit different, right? Different in the sense that a binary tree is a tree that have at most two children, as we discussed in the binary search tree, right? So it can have either zero child, one or two children, right? So that's called a binary tree. So for example, if this is a tree, this is a root, it is a binary tree. This is also a binary tree. This is also a binary tree. But anything else with more than two nodes or is not a binary tree. So what's the difference in binary tree and the binary search tree? So binary search tree is basically a binary tree, but with the property that the left child is smaller than the parent node, the parent, and the right child is greater than the parent. But here we don't have any such property. That is a special property of the binary search tree. But the binary tree is a tree that is basically having either zero child, one or two children, right? That's called a binary search tree. Now, why do we study this binary search tree? Because we are interested to learn about the heaps. So heap can be implemented. Heap is basically a binary tree. So how it is a binary tree, how we can use it, just hold on, we'll discuss this. But before that, let's discuss some important properties of the binary tree. Properties of binary tree. Right, so um if I have a binary tree, okay, so in a binary tree, it could be complete binary tree or incomplete binary tree, or nearly complete binary tree, or the almost complete binary tree. What do I mean by this? So for example, if I have a tree like this, it has children, and then this also have children at if every node either has zero child or two children. If, let me just write it over here, every node has either zero or two children. If this is true, then this is called complete binary tree, right? Then this is called complete binary tree. Okay, like for example, this one that is given in this uh, that I have drawn here. So every node, it has either two children or zero children, means it is a leaf node, right? If it is a leaf node, it will definitely have zero child. If it is not a leaf node, it will definitely have more than it will have exactly two children, right? So that's the that's the definition of the complete binary tree. Clear? So if the tree is like this, for example, this this one is this, like this, right? And then this node has one child, this node has two children, for example this one. So if this is the scenario, so you can see the nodes okay, so the node have two children. First node have root node have two children, but then the left node has only one child, and the right node has also two children. So if this is the case, where the left node have one child and the space is empty, so you can see this space is empty, right? And then the right child also have the children. If this is the scenario, this is called incomplete binary tree. Incomplete What do I mean by incomplete binary tree? Incomplete binary tree is when we have one node having no child or a missing child, and the next node have the children. So if this is the scenario, then this is called incomplete binary tree. Now what is almost complete binary tree or nearly complete binary tree? That is important. So if there is scenarios like this, the root node has two children, and then this also have two children, right? Left node has two children, right have one children or zero child, right? Whatever. So if this is the scenario, you can see the root node have children, two children, the left node has two children, the right node has one child on the left hand side, and right side is missing. It's okay. This is if this is the case, this is called almost complete binary tree, right? Or we call it nearly complete binary tree, right? So the definition of the nearly complete binary tree or the almost complete binary tree is if a node has missing last children, right? There is no gap in between. So you can see, if I see level by level, so at level 0 all the nodes are present, at level 1 all nodes are present, at level 2 all nodes are present except at the last one. So if it also have the child, it has the children, right? It has a child like this. So at this level all the nodes are complete. At this level some nodes are missing, but the starting nodes are complete. If this is the scenario, then we call it the almost complete binary tree. But if the starting nodes are missing, any of the starting node is missing, and then we have another node at the last, means if we have a gap in between, that is called incomplete binary tree. Remember? Okay. So let's have few examples and see if the tree is the complete binary tree or not. Okay, so let me take the example. So for example, if this is a tree, like I have one node, another node, another node, another node. So is it a complete binary tree or incomplete binary tree or a almost complete binary tree? So you can see the root node has two children, fine, but the left node is having one child and the second child is missing, and then the right node is having a child. So it means there is a gap. So this is an incomplete binary tree, right? Incomplete. Fine. Okay, so if the scenario is like this, if I have a tree like this, this, so what type of tree is this? So you can see at every level, all the number of nodes are present. So this is a complete binary tree, right? Complete. Okay. Okay. So if I take one more example. Okay, how about this one? So you can see at this level all the nodes are present, at this level all nodes are present, at this level all nodes are present, at this level only one node is present, but that is on the leftmost position. There is no gap between the nodes. So this is almost complete binary tree, right? Okay, why we are going to study this? Remember, a heap, first thing, a heap is a almost or nearly complete tree, complete binary tree, right? So in order to study heaps, you must be clear what is a binary tree and what is almost or nearly complete or a complete binary tree. It could be complete, or it could be, the heap could be a complete binary tree or a nearly or almost complete binary tree. Fine. Now let's see. If this is a tree, binary, this is a complete binary tree, then what is time required to 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 access this element in this particular binary tree? I mean, what is the time if I insert the element, or if I delete the element, or if I search the element? So I'm so sorry. This is nothing but order of h time, right? So height of the tree, it is actually based on, depends on the height of the tree. Now let's see one more important concept. If so for example I am interested to know that if I have a complete binary tree, okay, if I have a complete, I'm talking about the complete binary tree, and then I'm interested to know that how much maximum node can be in a binary search tree. So I mean, for example, yeah, if this is the complete binary tree, right, like this one. Okay, so if this is the complete binary tree having only one node, so you can see this is also the complete binary tree, right? It's just root node and doesn't have any child. Okay, fine. So if I have only one node, right, so okay, I have only one node. What is the height of the tree? The height of the tree is obviously 0, right? Height of the tree is 0. Okay, if I have a tree like this, right, this is case number one. I'm talking, let me just make it clear. If I'm talking about this case, so what is the number of node, maximum number of node, and what is the height of the tree? The height of the tree is 1. Remember, what is the height of the tree? Height of the tree is from the root node to the leaf nodes with the number, maximum number of edges, right? So there is only one edge from root to leaf, one edge from root to leaf, so the height is 1. What are the maximum number of nodes? So the maximum number of nodes are 3, right? So nodes are 3, remember. So here height is 0 and the node is 1. Okay, and if this is the scenario, if where we have the height, what is the height of the tree? Height of the tree is 1 2. See, you can see all the way from leaf, root to leaf, the maximum number of edges are 2, so the height is 2. What are the maximum number of leaves? Maximum number of leaves are 1 2 3 4 5 6 7, right? So n is 7. So let me just draw one more tree. If the height of the tree is 3, then what are the maximum number of nodes? So if height of the tree is 3, what are the maximum number of nodes? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So the nodes are 15, right? So can we have some formula in order to find, given the height of the tree, if we can find what is the maximum number of nodes in a binary tree, right? So yes, there is a formula. So you can find the maximum number of nodes in a binary tree. If you know what is the height of the tree, the formula is 2 raised to the power of h plus 1 minus 1, right? And this whole with the floor function, right? 2 raised to the power of h plus 1 minus 1. So 2 raised to the power h plus 1 minus 1, how you can find this? Okay, so basically 2 raised to the power h. So for example, in this case, we were having only one, the height of the tree is 0. So if I substitute this 0 in this formula, what could I get? So I will get 2 to the power of height is 0, 0 plus 1 is 1, minus 1, that is nothing but 2 minus 1, that is 1. So you can see the number of maximum number of node is 1 here, right? So if I have if the height of the tree is 1, and what could be the maximum number of node? Let's substitute it in this formula. So 2 to the power of h is 1, so 1 plus 1 minus 1, that is nothing but 2 square minus 1. So 2 square minus 1 is what? That is 3, right? So you can see the number of node is 3, right? Let me just do this one. So if I have the height of the tree is 3, what are the maximum number of nodes? So if the height of the, let's just substitute in this formula, height of the tree is 3 plus 1 minus 1, so that is nothing but h to the power, okay, 2 to the power of, sorry, 2 to the power of 3 plus 1 minus 1. 2 to the power of 4 minus 1. 2 to the power of 4 is what? 2 to the power of 4 is nothing but 32. 32 minus 1, that is 31. Right? So the 2 to the power of 2 to the power of 4 is 16 minus 1, that is 15. So the number of nodes with height 3 is 15. Right? So this is the formula how we can find the maximum number of nodes in a binary tree if we know the height of the tree. Now let's see if we okay, so if we want to know the okay, now also you can find the height of the tree if you know the number of nodes. So for example, if you already know what is the number of what are the nodes present in a tree, you can find the height of the tree. So for example, if I say I have the number of nodes in a tree is 31, for example, so you can easily find what is the height of the tree. So that is the other way around. So the height of the tree you can simply find with the log of n base 2. So n is the number of nodes. So if I know the number of nodes, I can simply say what is the height of the tree. So for example, I can say I can find it out log of 31 base 2, that is nothing but 4, right, with the floor function, right? So that is 4. So for example, if I say I have the number of nodes present are 15 or 14 for 14, so you can simply find using the log 14 base 2, that is with the floor function, that is nothing but 3. So it's other way around. You can find the maximum number of node if you know what is the height of the tree, or you can find height of the tree if you know how many nodes are present in a tree. Clear? Now let's see one more important concept. That is if for example I have a binary tree, I have present a binary tree, and I am interested to know from where the leaves start in a tree. So for example, if this is a tree, if this is the binary tree, I'm talking about the complete binary tree or an almost or nearly complete binary tree. I'm not talking about the incomplete binary tree. So for example, if this is the complete binary tree, let me just explain the complete binary tree first, and then we'll discuss it. Okay, if this is the complete binary tree, and the indices are every node has one index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If this is the scenario and I am interested to know from where the leaf nodes starts, right? So how can I find this? So the formula is very simple. We can find it. So if we know the number of nodes in a tree, so we can say n, if n is the number of nodes divided by 2, right, with a floor function plus 1, right? The number of leaf nodes starts from here to n and it goes to n. So for example, in this tree, the number of nodes are 15. If I divide with 15 by 2, that is what? That is nothing but 7, right, plus 1. So 7 plus 1 is nothing but 8 to 15 are the leaf nodes. You can see 8, 9, 10, 11, 8 to 15 are the leaf nodes, right? So let's say for example, if I have the tree like this, right, this is also the complete almost complete binary tree, and the indices are like this, right? So I'm interested to know from where the leaf node starts. So how can I find the leaf nodes? Simply put into the formula, that is what? N by 2. N by 2 is what? 4 by 2 plus 1. So 4 by 2 is nothing but 2 plus 1, that is 3. So leaf nodes starts from 3, 4, these are the leaf nodes. So so for example, if I have more nodes in here, 5 and 6, right, I am interested to find the leaf node from here. So you can see that is nothing but 6 by 2 plus 1, right? So 6 by 2 is nothing but 3 plus 1, that is 4. So leaf nodes now starts from 4, right? So if I have few more nodes, 7 and 8, right? Now I'm interested to find the from where the leaf node starts. So the total number of nodes are 8. 8 by 2 plus 1. So 8 by 2 is 4 plus 1. So leaf nodes starts from 5. So you can see 5, 6, 7, 8 are the leaf nodes. So if I have one more node and the total number of nodes are 9 now. So you can see what I can do is 9 by 2 with a floor function plus 1. So 9 by 2 is nothing but 4.5. With a floor it's 4 plus 1, 5. So leaf node still starts from 4, 5, 5, 6, 7, 8, 9. These are the leaf nodes. But if I have one child of 5 as well, the left child, this is the left child of 5. So, and the index is 10. So now you can see 10 divided by 2 plus 1. So that is nothing but 6. So leaf node starts from the 6. Right? So if I am interested to know from where the leaf node starts in a complete binary tree or in a almost complete binary tree, so the formula is n by 2 plus 1 to n. So leaf node starts from n by 2 plus 1 and it goes up to n. Clear? And if the other way around, if I want to know what are the non-leaf nodes, so from where the non-leaves is from where to where are the non-leaf nodes. So the formula is very simple, right? So what you can do is this is to find the non-leaf nodes, right? Leaf nodes. This is for leaf nodes. So for non-leaf nodes, what should I do? What should I do? For non-leaf nodes, what I can do is total number of nodes, right? N, okay, obviously it will start from 1. The non-leaf nodes will start from 1 to n by 2. If it starts from n by 2 plus 1 are the non-leaf nodes, so 1 to n by 2 are the leaf nodes. So you can check. For example, here total number of nodes are 10. So 10 by 2 is 5, right? So 10 by 2 is 5. So from 1 to 5 are the non-leaf nodes. Clear? Similarly here, the total number of nodes are 15. So n by 2 is, this is also with the floor function, n by 2 is 15 by 2, that is 7. So 1 to 7 are the non-leaf nodes, right? So to remember these two formulas, we will be requiring these formulas when we are going to write the algorithm for heap and the build max heap. Clear? So this is how we are going to find the leaf nodes and the non-leaf nodes. Now let's define what is a heap. Okay, so heap data structure, there are two things. Number one, it's almost complete binary tree. Binary tree, what does it mean? I will explain. You are very much clear now about the complete binary tree, right? If not, rewind the video. Okay, one thing. Second thing is second thing says that whatever is the value of the parent at every node, right? It should be greater than or equal to the current value if I am talking about the max heap. Okay, what does this max heap now? So I will just explain. Just hold on. And the value at parent of I will be smaller than or equal to array of I if it is a min heap. What does it mean? It means we have two types of the heaps. One is called the max heap, and other is called min heap. Right? Max heap and the min heap. What is the max heap and what is the min heap? In a max heap, remember, in a max heap, so for example, let me just draw it. In a max heap, okay, number one, it is a almost complete binary tree, or it could be a complete binary tree. But the thing is, in a max heap, the parent node will always be greater than both of its children. So what does it mean? The parent node will be greater than its children, right? All of its children. The parent is greater than its children. Every node 6, here 9 is greater than its children. Here 6 is greater than its children. 8 is greater than its children. So if this satisfies, then we call it a max heap. So max heap is when the parent node is greater than both of its children and it is implemented as a binary tree, we call it a max heap. Clear? Okay, and one more thing is the maximum in a max heap, the largest value is at the root, right? So the largest value is always present at the root. Now let me talk about the min heap. In a min heap, the same thing is happening, but in a reverse order. So the root node at the root, okay, the parent is always smaller than both of its children, right? The parent is smaller than its children. So here you can see the parent is smaller than both of its children. The parent is smaller than its children. The parent is smaller than its children, and it is implemented as the binary tree. So if this is true, then this is called min heap, and the minimum value will always be at the root, right? So this is how we define the max heap and the min heap. What is max heap and min heap? Number one, it's a complete or almost complete binary tree. Number two, if it is a max heap, the parent is always greater than both of its children, right? And if it is a min heap, the parent is always smaller than its children, right? In a max heap, the largest value is at the root node, and in a min heap, the smallest value is at the root node. Clear? So this is how we define it. Okay, then my question is, since this is a data structure, why do we need this data structure? Since we have many data structures, right? We have studied the array, we have studied the linked list, we have studied binary search tree, and many others. So what is the need of this heap data structure? So let's understand this first, that what is the need of this heap, right? So for example, if I am using why do we need data structures? Because we need to perform several operations on the data, right? So for example, what sort of operations we perform normally? We perform the dictionary operations, right? So what are the dictionary operations? Insert, delete, find max, find min, search, and all the operations. These sort of the operations are called the dictionary operations that are being used in the in databases, and we need to implement using the data structures in efficient way. So the efficient data structure is required. So let me say, if I want to perform some operations, so for example, I want to insert some element, right, into the and I need to select the data structure for that. I want to search an element, right, or find the element, and I am interested to find the max or the min value from that particular thing, right, from that data, and I want to delete the max and min value, or like we do in the priority queues. So for these operations, right, for these operations, what should I do? If I use the array, right, and in an array we can use sorted array or the unsorted array. Let me say if I am using the unsorted array. If I use unsorted array, what should be the time complexity of each operation? So in an unsorted array, if I want to insert an element into the into some location, so what is the time complexity? So time complexity should be order of 1, right? It's nothing like, for example, if I have uh, an array and I have some values in the array 5, 1, 2, 6, 9, 3, 4, and I want to insert one more element. What should I do? Simply go at the last and insert that value. So for example 8, right? I will simply insert. So that's nothing but order of 1. But if I want to search some element from the from this array, what should be the unsorted array, what should be the time complexity? So I will use the linear search methodology here, right? I cannot use the binary search, so that would be order of n, right? If I want to find the maximum value, if I want to find the maximum value or the minimum value from this array, so I have to go one by one. I have to compare this with this one, this one, this one. I have to do all the comparison. So as a worst, it will take order of n time. And if I want to delete a value, if I want to simply delete a value, I need to search that value. So in order to search, I need the order of n time plus 1 to delete it. That is order of n. And if I want to delete maximum value or the minimum value, again I need to search the max value or the minimum value from the array, and that require order of n time. And then to delete it, that require order of n plus 1. So that requires order of n time, right? Instead, if I use sorted array, so what should be the cost of each operation, right? So if I use a sorted array, if I want to insert some element, so say for example, understand, if I have this sorted array with me, say 1, 2, 3, 4, 5, 6, 7, 8, and now okay, say for example, let me add few more elements, 12, 15, 30, right? And now I want to insert 9. So what should I do? I need to create the place for 9. First of all, I need to find the place of 9, and I have to create the place. I have to make it empty and move all the elements there. So first of all, what I will do, I will find the place for 9, like the insertion sort. So I will come to the point that, okay, here is the place of the 9, and I will move all the elements forward 15, 30, right? And then I will insert 9 here, right? So it requires order of n time, right? Order of n plus I have to, first of all, I have to search, and then even if I use the binary search for the sorted array, even then I need the log n time in order to search. And then for example, if it is here, so then n times I need to move the elements, right? And then to insert it. So for example, the log n time for the binary search plus n time to move it, and then 1 to insert it. So if I take the big O, that is nothing but order of n, right? And for sure, for the searching, I can use the binary search, so that is order of log n, right? For the maximum value and the minimum value in the sorted array, if it is a sorted array, we can implement it using the binary. Okay, and then the minimum value, if it is sorted in the ascending order, the minimum value will be on the at the first location, and the maximum value will be at the last location, at the nth location. And if it is sorted in the descending order, the minimum value will be at the nth location, and the smallest value will be at the first position. So that is nothing but order of 1 time, right? And similarly, if you want to delete it, if you want to delete the min value from the sorted array in the ascending form, so if say for example here, if you want to delete 1, right? So what you need to do, simply you will delete it, and you need to shift all the elements back, right? So that requires n movements. So that will lead to the at maximum order of n time, right? So if you want to delete it, it requires maximum order of n. Okay, now let me talk about the linked list. If I am using linked list, right? So how much time each operation will use? So if I am using the linked list, in order to insert anywhere you can insert, right? That requires order of 1 time. You just need to update the pointers. In order to search, you cannot search using the binary search method. You have to go linearly, that is order of n. Find min, find max, obviously linearly, order of n time. If you want to delete, any element, then it is order of 1. You need to search it first. In order to search, you require n times, so that is order of n, right? And we have also studied the BSTs, right? BSTs, binary search trees. So in order to, if we implement the binary search tree, what will happen? So in order to insert, we already see the algorithms of the binary search tree. So that require order of log n, right? In order to search, we know order of log n. In order to find the max and minimum value, we require log n time, right? Uh, and for deletion, we know that it's also require log n time. We know in the previous videos we have seen these algorithms. Now I want some efficient data structure where I can implement these operations in constant time. For some of the operations in the constant time. For example, for that I need heap. So if I use the heap data structure, right? If I use the heap data structure, what time will be required? So we'll prove this in the upcoming videos. So in order to insert in a heap, we require log n time. In order to search, right, we require, okay, we don't actually search from the heap, but if we want to search, this will require order of n time. But in order to find the min value and the max value, I show you that in a max heap, the maximum value is at the root, and in the min heap, the minimum value is at the root. So you can easily find it in order of 1 time. So you can easily delete it in order of 1 time as well, right? So you can insert, you can update, and you can delete it in an efficient time. So that's why we use a heap whenever we are going to do we are performing such operations. For example, we are going to implement the priority queues. For implementing the priority queues, we use heap data structure. We know that in the priority queue, what we actually perform, we find the min value or the max value, having the values having the minimum priority and the maximum priority, and we can easily implement using the heap data structure, right? So this is how we actually what is the need of the heap data structure. Now let's see how we can represent this by max heap or the min heap using a array. So for example, if I have a tree like I have in the previous example, if this is a max heap, I can during the implementation or the programming, I really don't need to implement it as a tree. I can represent this max heap or the min heap using an array. So how we can do that? See, we can easily implement this in an array, right? And we insert the value in the array level by level. So at the first level 0, I have 9, I just inserted it. At next level, I have 6 and 8, I inserted in the same order. And next, at the next level, I have 5, 4 and 7. I can simply insert like this, right? But then the question is, how do we maintain the relationships of parent and child, right? So let's see, if this is index 1 2 3 4 5 6, 1 2 3 4 5 6, I'm using the index from 1 because it is easier to represent now here, but we can use from 0 as well when we are going to implement it as a programming. Okay, so what is the relationship between parent and child? How we can maintain the parent relationship? So if you see, if I want to find the child of this node I, that is 1, so the left child of this node is 2, right? And if I want to find the left child of 2, that is 4. If I will find the left child of 4, that will be 8. So that means if I am going to find the left of I, some left child of some node I, that is very easy. How we can find the left of I? That is nothing but 2i, right? So simply multiply it with 2 and you will get the parent, so the left child, so 2 times I, right? So multiply 2 with I and you will get the left child. So how I can find the right child? You can see the right child of 1 is 3 and right child of 3 is 3 should be 7, right? So if you are interested to find right of I, so you can easily find it with 2I plus 1, right? So you can see 2I, if I am interested to find for the node 1, 2 plus 1, that is 3. For the next level, 3 times 2, 6 plus 1, 7. So you can see the next would be 7. So if I am interested to find the right child of 6, so 6 times 2 is 12 plus 1, 13. So it should be 13. You can draw and you can see the right child of 6 will be of the index 6 will be 13, right? And similarly, if I am interested to find the parent of some node, right? If I am interested to find the parent of 5, I am interested to find the parent of 6, I am interested to find the parent of 4. So that also you can find. If I am interested to find the parent of some node I, that is nothing but I divided by 2 with a floor function, right? So for example, if you are interested to find the parent of 6, that is nothing but 6 by 2, that is 3. You can see parent of 5 parent of 5 divided by 2, that is 2.5. If you take the floor, that is 2, right? Parent of 4 divided by 2, that is 2. Parent of 2, that is 2 divided by 2, that is 1. Parent of 3, that is 3 divided by 2, 1.5, floor 1. So the parent can be easily found using this formula, using this way. So this is how we maintain the relationship in the array. So if I want to find the parent of one, the child, left child of 1, that is 2 times 1, that is 2. This is left, this is right. 2i plus 1, right? If I want to find the left child of 2, that is 2 times 2, that is 4, right? And the right child of 2, 2 times 2 plus 1, 4 plus 1, that is 5, like this. I am interested to find the parent left child of 4, that is 4 times 2, that is 8. That is not present in the array, that's it. For the 3, if I am interested to find the left child of 3, that is 3 times 2, that is 6, right? So this is how we are going to maintain the relationships. And if I am interested to find the parent, simply parent of 5 divided by 2, that is 2, floor, take the floor, that is 2, right? So this is how we are going to maintain the relationships. Okay, similarly we can implement the min heap using the array. So for this min heap, you can implement it using the array. 1 2 3 4 5 6 7, right? So you can easily implement using the min heap using the array, and the relationship is maintained similarly. One thing you must note is either it's a max heap or a min heap. It's sorted, isn't it? So if it is a max heap, it is sorted in decreasing order, and if it is the min heap, it is sorted in a non-decreasing order, right? So it means if you want to represent some data as a heap, you can sort it, but then sorting the best sorting algorithm, whatever you take, it requires order of n log n time, isn't it? Right? So we have to find the efficient algorithm. We have one algorithm that sorts it, that makes it a heap in order of n time, and we will study this in the next video, that is called Heapify. So we will study the Heapify algorithm in the upcoming video, that will make this any given any given binary tree, complete or almost complete binary tree, into a heap. If it is a max heap, we use the max heapify algorithm. If it is a min heap, we use the min heapify algorithm, right? Okay, and then one last thing for this video is, if I am interested to add or delete some node insert some node or delete some node in the heap, that what should we do? So for example, if some data is given and you want to some heap is given. So for example, if this heap is given, right? This heap is given, and you are interested to add a new node 10, right? Okay, So you cannot add 10, by the way, because it will violate the property of the heap, because the root node should be the greatest one. So say for example, if duplicate values are allowed in the heap, right? So say for example, if I want to insert, okay, I want to insert, let me just redraw one more heap, easier. Okay, so for example, if I this is 100, right? This is 95, and this is 90. This is 85, 80. This is, for example, 75 and 70. This is, for example, 65, and I want to insert 60. So how you are going to insert it? So you can easily insert it at the last, after the last node. So what's the last node? Obviously you can find it the last, the size of the heap, and at the end you are going to insert it, right? And if you want to add one more, so for example 50, so after this you will go and you will insert 50 in the leaf node, right? And if you are going to insert, so for example 40, you will add at the end. And then, say for example, if you want to add 200, so obviously you will go to at the end and you will add 200 here, but then it violates the property of the heap, because the parent node should be greater than this child. Then we need to fix it. In order to fix this, we will use this heapify algorithm, right? So remember this, if we are going to insert some node in the heap, that will always be inserted at the last node, right? We cannot insert here in some other place immediately after the last node, and then it may violate the property of the heap. In order to maintain the heap property, we will heapify it. Clear? Similarly, if you are interested to to delete some node, so remember, you cannot insert the intermediate nodes, you can only delete the root node. So in a max heap, you can always delete the maximum value. So the max node will be deleted. In a min heap, root node will be deleted, minimum node will be deleted. How we delete it? We'll swap this value with the last node, this node with the last node, and then we'll delete this node, and then this may violate, this will definitely violate the property of the heap, and then we'll fix this using the heapify again, right? So this is all about this lecture. So in this video, what actually we did, we discussed about the binary trees, that what are the binary trees, complete binary trees, almost complete binary trees, right? And we discussed the properties of the complete binary trees, that how we can find the maximum number of nodes in a tree, how we can find the height of the tree, what are the from where the leaf nodes are starting, from where the non-leaf nodes are starting, and then we defined the heap, that heap is a binary tree, right? And also we discussed about the max heap and the min heap, and we discussed that why do we need the this heap, and also we discussed the array representation of heap, right? And we saw that how we can find the maintain the relationship in the array, the left, right, and the parent node, how we can find it. And at the end we saw how we can insert and how we can remove the nodes from the from a heap, right? So in the next video I will talk about heapify and how to build a max heap or the min heap. Thank you.